to another episode of Planet Hunters Coffee Chat. I'm your host, Cassie Prolongo, and of course, joining me as always, the lovely Nora Eisner. Good to see you, Nora.
Good to see you, Cassie. I feel like it's been a while.
It has been a while. You and Cole did an amazing job last episode when you talked about astroseismology. Thank you again to Cole, our resident and friend of the pod, for his incredible work and hosting it. And thank you as always for joining us. So we talked about this before. We are going to continue filming. Obviously for today, we're going to film another episode that's coming up. And then we're coming up to the summer. So we're going to take a little hiatus again. Nora and I are going to reassess how we want to plan our episodes moving forward. And the cadence of our episodes is going to change in the future. So that means probably not weekly. We might go to once a month. We might go to bi-weekly. We're not 100% sure yet. As always, just send in your requests of what you want us to film. We have a few that are in the queue. We've been looking at the YouTube channel and all the things that you guys have been submitting. So just keep submitting your ideas and we'll get that done. So that being said, we did radial velocity, astroseismology. What are we moving into for today, Nora?
So today we'll combine a couple of things that we've talked about. We'll briefly touch on astroseismology and radial velocity and transits, because we love transits, they're our favorite. So we'll look at a candidate that I have talked about so much that I'm assuming, Cassie, you have memorized this TIC ID by now. So I'll say it really quickly and we'll see whether you remember it. Okay, it's TIC 555-25572.
555-255-72.
Yes, see, you've had it enough. That was good.
Get it? I'm going to have it tattooed right here so that when I look down, I'll be like, yeah, that's memorized. Totally.
Yeah, totally. You didn't write that down at all.
No, I don't have it on my wrist, you guys. I'm just kidding. But seriously, that would be a real good cheat sheet, I think, to do that. Yes. So your favorite TIC ID, and we know why it was your favorite TIC ID. Is this the same one? Was this or is this a different one?
I don't remember. I think maybe we've said this already. This is not a very exciting reason as to why it's my favorite one. It's just my favorite one because it was Planet Hunters TESS's first planet. So it's always got a place in my heart.
Yeah, it's the nostalgia of it.
It's also a really cool planet. So we'll look at that today and we'll talk about some of its properties. So to do that, I've prepared a notebook. So we'll look at that and we'll hopefully see quite a few ideas and kind of just things that we've already discussed in the episodes over the past year.
Nora, I didn't show you my coffee mug for this time. I think you would appreciate that because it's a super cute animal. Can you see it?
Oh, what is that a cat? A rabbit?
I think it's like a little cat or a rabbit. I can't really tell, to be honest with you. I think it's a cat because it's got a tail.
I also have I've got a fox.
Oh,
this is the one where last time you thought it was a light curve.
I thought it was a light curve. I swear. I'm like, getting old is great. I totally don't need glasses or anything. I'm like, it's a light curve, right? And Nora's looking at me like, are you insane? No. Now that I see it, it is definitely a fox. Yeah, let's go with that one. Mm-hmm.
Okay, cool. Yeah, I will just go through the notebook and we'll hopefully see lots of things that we've already talked about. So so do link back to some of the things that if we go through some of the things a little bit too fast, do maybe just go back to the old videos and watch those. All right, so at the beginning, we're just importing all the modules like we always do. And we're going to use our favorite tool, Lightcurve, to download the data. So we're doing that here. We're defining the TIC ID 555-25572. And downloading this is the 2-minute cadence data. So I'm not sure if we've used this before. This target was also observed at a 20-second cadence data. So in this case, we just want to say we don't care about the 20-second cadence. We just want to look at that 2-minute cadence data. So I've added in this one line here, this exposure time equals 120 in seconds, which is 2 minutes. Cool, then we're downloading it, I am binning it, and here in the next line, I am plotting it, and we can see we have lots and lots of data. So, and I should also say in this case where I'm showing both the unbinned and the bin data, and the bin data is shown at the 30-minute cadence, which is shown in red. And what we can see here, it's a little bit hard to see because there is so much data and it's all kind of crammed into this one figure. But there are periodic dips in this light curve and they're separated by about 84 days. And we can see some of them, but others have have kind of been lost a little bit. But if we zoomed in, which I'm not going to do right now, but if we were to zoom in, we would be able to see those nice transits. And we have already seen those transits of this particular target, because I go on and on and on about this target in some of our other episodes.
Check out past episodes, exactly.
Yeah, so if you were to zoom in, you definitely would see those transits, but we're not going to do that right now. You just have to believe me that they are there. And they are separated by 84 days. So to put that into a bit of perspective, that's roughly the orbital period of Mercury in our solar system. So Mercury, which is the innermost planet, has an orbital period of 88 days. So it's just a little bit shorter than that, but in terms of the planets that we find, it's quite long, but we'll come back to that in just a moment. Okay, cool. And I said we weren't going to look at the transits. I actually lied. We are going to look at the transits. So next we're going to phase fold this light curve, which again is something that we have an episode on. So you have to define the period, you have to define the time of one of the transit events, and then we can use this light curve tool to phase fold. And we can do that and we can plot it, and there you can go. You don't only just have to believe me, you can also just see that there is a transit there, which we can see. All right, the cool thing about that is that we can use this light curve, this phase folded light curve, to determine the depth of that signal, and the depth can tell us about the size of this planet. So it can tell us the radius of this planet orbiting around this star. So again, something that we've already done. So we're doing that here. We're saying this is the depth. Or this is the point at which kind of the bottom of this is. So we want to look at kind of the midpoint of all those scattered blue points, which is roughly here. We can read that off, and then we just do 1 minus that to get the kind of the depth. So to get for the distance between this flat part of the light curve and the lowermost part. And then if you remember, if we want to know the size of the planet, we need to know the size of the star. Very important. This is something we kind of touched on last episode as well with astroseismology. You want to know the properties of your star to know the properties of your planet.
Right.
In this case, we're getting those from ExoFOP. So we can just go to ExoFOP, look that up, and type it in here. We're also using a tool called astropy.unit. Again, something we mentioned briefly in a couple of episodes. A really, really useful tool. It means you don't have to do your own unit conversion. It means you can say, this number here is in units of the sun, but now I want them in units of the Earth. And it will just do that automatically for you and make sure that everything lines up. But if you want to use this notebook for a different target, you just have to change this number here.
Yes.
Cool.
I know we've mentioned this before, but ExoFOP is seriously, it has become like one of my favorite resources to go to. It's a cool website. And there's just so much great information that you can look up there.
No, absolutely. ExoFOP is, I completely agree, is so useful. Yeah, really good tool. I use it all the time. It's also the one I use the most.
And if an astronomer is saying that, then you know that means something. So definitely check it out. And it's just very user-friendly. You know, as somebody who's not an expert in this, but is just a citizen scientist, it's just user-friendly to use.
Yeah, absolutely. Yeah. Cool. So I've also written a little function here that basically just tells us what the size of this planet is. So we just need to put in that transit depth that we had up here, that we've already defined, and the size of the star. And then it prints out what the radius of this planet is, which is around 7.34 Earth radii, which is cool. So it's, that's roughly what it is on ExoFOP as well. So that's always a good check if it is a known planet. But yeah, so that's already quite cool. So we already have one property of the planet. But if we want to kind of understand this property more fully, we want to also look at the mass. So knowing the mass and the radius is really useful because that gives you an insight into kind of the composition of this planet. How heavy is it? What's it potentially made of? And lets us answer kind of all these quite interesting questions and lets us place it into the context of either our solar system planets or other exoplanets that we have found. So this draws back on a previous episode that we did on radial velocities, which I think was 2 episodes ago.
2 episodes, yep.
So I call that step 3 in this. Step 3 is, step 3 is determining the mass of this planet. So if you remember back from the radial velocity episode, often you can find these measurements, these radial velocity measurements on the ESO archive, so the European Southern Observatory. We're not going to go over that again today because we have already done it. Instead, I have already downloaded the data and I have extracted the radial velocity observations and I've put them into a file, which you can download alongside this notebook from the website. So all we have to do is sorry?
I just said Nora's the best.
Oh.
Makes it easy. She's signposting all of this for you guys. It's super easy.
I try to be helpful. Yeah, so all we have to do is we have to import that file. It's just a text file, and it has columns that has the time, the radial velocity observation or measurement, and the uncertainty on that measurement. So we just import it. As you can see here, we then get a list of the times, a list of the radial velocities, and a list of the errors. Cool. The next thing we want to do is we want to plot those, and we're going to plot them phased. So luckily, in this case, we know what the orbital period is. We saw that from the light curve. It's around 84 days. Of course, we want that number to be a bit more precise than just the 84 days, but that's something we've already defined in this notebook, somewhere up here.
There it is.
We can find the period. So what we're doing is we're phase folding it and plotting it there. And hopefully you can see a nice S shape here, a sinusoid, which is exactly what we want, because that allows us to determine the mass of this planet.
Can I ask a quick question too? With the, you said we should be a bit more precise than the 84 days. If we don't, what was it? It was 83 point, and then I think it was off to like 3 decimal points.
Yeah, as many decimal places as possible.
889. Oh, okay. I was just going to ask, is it better to, well, obviously you can look it up and everything so that you know what the period is, but I mean, if you have it as 0.889 as opposed to 0.8889, will that mess up a lot of the calculations? Should you have it be as precise as possible is what I'm trying to get at.
Yeah, you want it to be as precise as possible. So the amount, the kind of the precision, the number of decimal places you can have will depend on how much data you have. So if you have a longer baseline, if you have data over 5 years, you can get that number to much better precision than if you just have 2 transits. So over the 84 days. So we can show that here with the transit data. So this is what it looked like when we have a good idea of what this value is. But if we, for example, change this to 0.7 or something and let that load, we'll be able to see that that's already very much out of phase. So it starts to shift by quite a large amount. So you can play around with this number if we just do undo. See what happens when we just change this last number. It probably won't change very much. I don't know, change this to a 5. Maybe it will change by a large amount. You can see, change it by a little bit. You can see it's already slightly shifted, so slightly incorrect. So playing around with that number will help you get to the right amount or to that right value. And because we have so much transit data, we can get that number to quite a good value.
Yeah. That's why this is a good candidate that you're working with this one, with this TIC ID.
Okay. Another reason why it's a good candidate.
Yes, it's a good example one. Okay. Thank you for answering a slight side tangent. Back to our regular scheduled programming.
Yeah, no, it's important to get all these numbers as precisely as possible. Okay. All right, so now that we have our nice face folded light curve, we're going to try and fit a very approximate model to it so that we get an idea of how high this signal is. So if you remember, the kind of size of the signal, the amplitude of the signal tells you how heavy this planet is in relation to the mass of the star. So we can do that here. I've already entered these parameters. You can find these in the published paper. Maybe you can find them on ExoFop. I'm not sure if you can find them on ExoFop, but you can definitely find them in the published paper. And we can face fold it and draw this nice orange line to it. Okay, and from this, the important part is we have the amplitude of the signal. So that's, for some reason, it's denoted by a K, which is 5.96. And we can use that to get a mass of the planet, which is the thing that we want. And I don't know why that's not in here, but that is in the other notebook. I'll put it into this notebook too. You can convert that K value into a simple mass of the planet if you know the mass of the star, and you can get the mass of the star from ExoFop.
Another plug for ExoFop. I swear, maybe we should be sponsored by ExoFop.
I think we should. People are going to think we are.
Yeah, we keep bringing it up so much. It's a useful tool, dang it. Not sponsored by ExoFop. And then a clever banner will be at the bottom of our screen. Okay, so step 4. Now that we have the mass and the radius, we can work out the density of the planet. Okay, so now we're getting towards the end.
Yeah, so this is the last step that we'll do for today. So this is kind of the new part. So what, as I already said before, mass and the radius are two of the most fundamental properties that we care about exoplanets, because they do let us compare them to other property or to other exoplanets that are out there. So what we're going to do is we're going to download a list of all of the known exoplanets. And what we're going to use is we're going to use the exoplanet archive. So that's the exoplanet archive.ipac.caltech.edu. So unsurprisingly, it is run by Caltech. Mm-hmm. And it's really, I will put the link in the chat, in the description of the video as well. It's a really, really useful tool. So if you scroll down to the bottom here, well, at the top, I'll start with at the top it gives you some kind of overview numbers. It gives you a number of confirmed planets. That's today is 5,035 TESS confirmed planets and TESS candidates. So if you're ever looking for these numbers to tell someone, this is where to find them. Yes. But what we're looking at here is, if you care about TESS only, that's you looking at this pink box on the left. But for now, we want to look at all of the confirmed exoplanets. And those are in this work with the data box here on the bottom right. And I use this planetary system composite table. So if you click on that, we will get a really, really long list of all of the confirmed exoplanets known to date. So here at the bottom, you can see that there are 5,035. And this is such a cool database because it lets you kind of filter by different things. You can filter, for example, you can say, I only want the transiting planet. So you can type in transit, and you're given just a list of the transiting planets. You can see that's 3,880 out of the 5,035. You can say, I only want the planets found in 2009. Don't know why you would want that, but maybe you do. You can sort by all these different parameters and just find out what these numbers are. And it'll give you a reference at the back as well in one of these columns, which directly links you to the discovery paper. So if you want to find out even more about it, you can also have a look at those. Oh, and if those columns that you're seeing here aren't enough for you, you can also add more columns. So you can click on this button here in the bottom left, top left, and add whatever columns you want.
Oh my God. If you like Excel and if you like dealing with Excel, then you will probably love this. But this is extremely useful. I love that they have the filter functions set up with this. This is another one of those. It's great. I haven't gone through like to the extent that you have with all of this data, but I have gone to this website. I've looked at some of the documentation, the videos. Another great resource to have. Like just have it. You know how you can make tabs and you can just put on your bookmarks bar. This should just be bookmarked. This Exofop and gosh, what are one of the other resources that we use quite a lot? I'm completely blanking on. Which one?
Sinbad, maybe?
Yes, Sinbad. You should definitely have those as your top 3 when you're looking up things. Okay, cool. So do you have to import or export this table?
Yes. So we want to export it. So export it when you haven't selected any specific thing, unless that's what you want. So you want to, at the moment, what I want or what we want is we just want a list of all of the confirmed exoplanets. So get rid of any filters and then just go to download table and download it in the CVS format, which is the standard, and just do download table. Okay. And this will be downloaded as an Excel file for you.
Great.
All right. So I've already done that, and you can do that yourself. It comes up with a name that is something like this. So you can see that I did this today because this is the day that we're filming. And we just have to import it. So you have to make this path link to wherever you save it. So if it's in your download folder, that path needs to link to, for example, user Cassie downloads, and then that name or wherever you've saved it on your computer. Yeah. That's the only thing you need to change in this notebook. You have to download that file and change that path. And then you can import that file. Then there's going to be lots of code because we have defined the mass of this planet is 48 Earth masses, which is something I didn't calculate above, but should have. We are now converting that into Jupiter masses. So we're going to do the rest of this notebook in Jupiter masses. For no particular reason, you could also do this in Earth masses. It doesn't really matter. Yeah, they're just a direct conversion to one another. But for some reason, we're going to work in Jupiter masses. So we've got the size of it, we've got the uncertainties, and we've got the radius and the uncertainties of those. The reason we want the reason we want those is because we're going to plot them in just a moment. But before we do that, I've also applied another filter, which is going to sound a bit weird, but will make our plot look a lot nicer. So what we're going to plot is we're going to look at all of the transiting planets that have been confirmed, but we're only going to look at the transiting planets that have a good mass measurement. So there are lots and lots of transiting planets around really, really faint stars that are just really difficult to get a mass measurement of. So we don't want to plot those because they will be difficult to put into the context of the greater exoplanet kind of demographic, because we don't have a good idea of what their properties are. So we just want to look at the ones that have a mass measurement with a precision of at least 30%. So we want a mass measurement where someone said, I know the mass of this planet to at least 30% its value. Otherwise, we're not going to plot it and just ignore it for now. So this function here calculates that percentage error for us. So you don't need to change anything in there. We're just going to calculate it with these lines of code. And we're going to say less than 30% is precision are the ones that we want, and just the transiting ones for now. And the reason we want just the transiting ones is because if they're not transiting, we don't have a good idea of what the radius of this planet is. So what I'm getting down to, what I should have said at the beginning, is we only want to plot the planets on this next figure that I'm about to show that have good mass measurements and good radius measurements. The other ones we're just going to ignore.
Yeah, so too long didn't read. If it's not within this parameter, it would throw off the entire thing that you're trying to do. Okay.
Yeah, it will just make our plot look a lot less tidy.
Yeah, we want a tidy plot. We like a tidy plot.
Do. Cool. So that's kind of what we're plotting here. So on here we have the radius over here and the mass down on the bottom. I don't know why this is so small. It doesn't matter.
Radii. Not in Earth, it's Jupiter masses still.
Yes, so we're just going to do the rest of this notebook in Jupiter radii. I should say this plot will look, the kind of distribution of these points will look exactly the same if we did this in Earth radii. The numbers would just be slightly different. Okay. But it doesn't really make a difference. So in gray, we have all of these confirmed planets listed in the NASA Exoplanet Archive that are transiting and have a mass measurement to at least 30% precision. And in blue, we have our planet. So TIC 5552557 And what's really cool about this is that we can see that this planet here, this planet that we're looking at, is in this in-between region. So we seem to have different populations on this figure. We have the ones that are up in the bottom top right-hand corner, this big cloud up here, and we have this relationship down here in the bottom left-hand corner. And then we have kind of a sparsely populated region in the middle, and that's where our planet falls, which shows that this is kind of a more unique planet. It stands out in terms of its properties. So this is kind of the main reason why we plot it against the other exoplanets, to see whether it stands out in any way, and to see how it compares to other planets. So we can use these mass radius diagrams. They're used for lots and lots of different things. They can tell you about the composition. They can tell you down here, we have the rocky planets. Up here, we have the gas giants. So we can tell you about what this planet is and potentially some insight into the formation. So this is it's known as a transition region between ice giants and gas giants is where this planet falls.
And that's why it's interesting, because it's in the in-between state, so to speak, in between.
Yes. Mm-hmm. Yeah, so there are some questions as to how these types of planets form. So it's good to find more of them, which is very, very cool. Mm-hmm. And also I didn't mention that these lines indicate the planets and all the properties of the planets in our solar system, just as a comparison. So we can see it falls between Neptune and Saturn.
Very cool. Okay.
All right, we have a couple more plots, so we can also show this in other ways. So another way of showing the properties, kind of comparing the properties of different planets that we're doing here, is instead of having mass radius, we can have the period versus radius, again, of those planets where we know the properties quite well. So what this shows is that most of the planets that we know are further to the left of this figure. They're shorter period. This is something that we've touched on quite a few times. And our planet is a long period planet, or much longer period planet, and is much further to the right, which again makes it stand out in terms of its properties and makes it another unique planet and a reason why it's It's very interesting. At the time that we published this, interestingly, it was the longest period planet that had been identified by the TESS mission. So that is no longer the case at all.
Yeah, I was going to say that must have been years ago, at least. Yeah, yeah.
Well, 2 years ago.
Oh, no, was it? Okay. For some reason, I thought it was 4 or 5 years ago. I don't know why. So this was the longest one, though.
Yeah, at the time. Absolutely not anymore. But it definitely was.
Exciting new discoveries happening all the time.
Exactly. Okay, so the final plot that we'll look at is, again, touching on something that we've discussed a little bit. We've discussed that stars go through different phases. So you can have young stars, you can have main sequence stars. We talked a little bit about the main sequence, and then you can have evolved stars. So finding planets, most of the planets that we know, just the vast majority of the planets that we know are around these main sequence stars. So we'll call them middle-aged stars. Yeah. But once they evolve beyond this main sequence, the radius of the stars increase, and generally the properties of these stars start to change quite rapidly. So studying the planets around these evolving stars is really interesting. So we want to know what happens to planets as the stars evolve. How does this affect the planet-star interactions? How does it affect the habitability potentially of planets? And just overall what happens to the system. So this star here, TIC 555-25572, at this point I'm just proving that I know this number, is a slightly evolved star. It is, we call it a subgiant. And what I want to show also is that planets around subgiants are quite rare. So on this next figure here, we're going to only look at planets around evolved stars. I'm just going to scroll down to the bottom of this code, and we're going to look at planets around evolved stars that were found using the transit method and that were found using the radial velocity method. And we're going to look at it in terms of the stellar radius, so the size of the star, and the period of the planet. So we have the radial velocity planets there on the right and the transiting planets on the left. And our planet here is the cross in the middle. So what this shows is that we have found quite a few very short period planets that transit. So those are shown in green or in teal there on the left. And we found really long period planets using the radial velocity method around evolved stars on the right. But there are quite a few missing in the middle. So this is another region in between these. These are the intermediate period planets around evolved stars where there's just not that many of them. They're quite difficult to find, but we can find them with Planet Hunters TESS, as we can show with this black cross. So
these are kind of the, this is like the Goldilocks sort of thing where it's not on either side. It's in that in between. We need more of these types of discoveries to happen in looking through the data. But they're hard. They're like you just said, they're hard to detect, basically.
Yeah, they're difficult to find, but they will help us kind of understand what happens to that planet-star interaction beyond the main sequence. And we do want to know that because all of our solar system planets will also go into that post-main sequence evolution at some point. Not anytime soon, don't worry. We still have a couple of billion years left, but
oh, is that all? That's fine.
Yeah.
Like, I don't have to pay my credit card debt off. No, I'm just kidding.
Yeah, so kind of what I wanted to show with this is the power of the NASA Exoplanet Archive. There's a lot of information on there. I've just shown a couple of the properties that we can plot. Period, radius, and mass are the important ones. And it's always good if you're finding a planet to compare it to other planets, just to see whether it stands out in any way. Brightness is another good one to look at. So the brightness of the star, the magnitude of the star. Yeah, just to see how it fits into the greater picture, I think is the overall message of this.
Yeah, no, and it's great. And as we always say, just play with the data, have fun with it. Nora did an amazing job just going through she's going to have this uploaded onto our website and Jupyter Notebook, and look at the resources that are available. ExoFOP, as we said, Sinbad, but that we didn't use that for this episode, and the NASA Exoplanet Archive. Have a look through the data. Just have fun with it. You're going to be okay. You're not going to break it. Yeah, great episode. Wonderful breakdown, Nora. Some of it was a little complicated, but I think going back and reviewing some of our other episodes, again, with radial velocity and all the other things that we've talked about before, are good refreshers. Obviously, we couldn't go through those things in depth because this would have been like a 2-hour episode. So just go through some of our past ones for that. Excellent breakdown. Anything else that you want to mention for this episode, Nora, before we shut down for the day?
No, I think you covered it all. I think, yeah, watch the previous episodes, and yeah, the notebooks will be available online. I realized I skipped through quite a lot of the code. There is a lot of code in there that you don't need to change, but if you're interested in playing around with that, I would recommend that you do so. I'll also add a little bit at the end that shows you some of the other columns that you can use to plot, maybe some simpler functions, but it should be enough to get started, hopefully.
That sounds great. Thank you very much, and thank you for joining us. And Nora, I guess I'll see you guys next week then.
Sounds good. See you next week.
All right.
Bye.
Bye.